Here we are with lesson 3 in our unit on one variable statistics, and we're looking at the measures of dispersion. So just to recall, we've already examined measures of central tendency, and those indicate the central value or the center point of a data set, so either the mean or the median, and also the value that's repeated the most often, which is the mode. But very often we want to know how closely the data cluster around the center. Okay, and these are known as the measures of spread or the dispersion of the data set. So measures of dispersion describe how far the individual data values have strayed from the mean, right? And this describes how closely the data values cluster around the mean. So some data sets will be very, very spread out. There's lots of variety in the data. Some data sets will be very, very close to the mean value. There are 3 measures of dispersion that we're going to investigate, and that's range, variance, and standard deviation. So here's an example. These two dot plots below each have a sample mean of about 54. Okay, so how would you describe the similarities and differences between these two samples, and why is it important to note the difference? Well, to begin, the means are similar. Okay, they're about 54. But the way the data behaves near the mean is very different for each sample. As you can see in the dot plot on the left, the data is very spread out. The dot plot on the right, the data is very close and very tight to the mean. Not a lot of dispersion. Sample 1 is more spread out, and its range is much larger. The range of data is much larger. So what are we looking for? Are we looking for variation, or are we looking for consistency? Because the mean can't tell us whether a data set is varied or whether it's consistent. So looking at range specifically, it's the simplest measure of dispersion. And it's calculated by finding the difference between the highest value and the lowest value of a data set. It's a very quick way to get a feel for the spread of the data, but it relies only on 2 data points to describe the variation. No other values between the highest and the lowest are involved in this calculation. So calculating the range on its own is very limited in what it can do for us. Variance, on the other hand, is a measure of dispersion that calculates the relative distance between the data points and the mean of a set of data. So the way that we calculate this is by squaring each deviation for an entire set of data and then finding the mean of those values. So a deviation is the difference between a data value, x, so some piece of data, and the mean, x bar. And if we're talking about a population, that's of course mu. And so really, it gives us a measure of, in general, what's the average spread of the data points. We'll see that when we look at population, n, which is the denominator in the population variance, is the number of data points in the entire population. And when we talk about sample variance, the denominator is n minus 1. Okay? And this compensates for the fact that a sample from a population tends to underestimate the deviations in the population. So a sample underestimates, and so we make a correction to the denominator. The reason why isn't important. It comes from some heavy-duty mathematics that we're not going to go into now. But that is a difference between sample variance and population variance. The standard deviation then really is just the square root of the variance. And so it really gives us the exact same thing, but it's more useful than the variance because the standard deviation is in the same units as the data set. What we just looked at before, the variance is in those units, but they're squared. So very often we'll talk about standard deviation, and it is more useful for our purposes than the variance. One thing you have to note is that everything that we've talked about so far is for ungrouped data only, right? So as soon as we put things into intervals, as we've done before, as soon as we group our data set into intervals and then we go with a frequency, these formulas change. So this is for raw data only. So here's an example, and really this is going to help us kind of grapple what this means. And so Miss Hughes and Mr. Jackson were hired to wrangle dinosaurs from the field so that they could be tagged with laser beams. Dinosaurs with laser beams. Team managers tracked how many dinosaurs we were able to collect, Miss Hughes and I, in each of the first 10 days on the job. And at the end of 10 days, those managers hired me on full-time because I collected an average of 53.7 dinosaurs per day. And unfortunately, they let Miss Hughes go because she only collected 53.6 dinosaurs on average. So now we want to say, okay, well, did the managers make the right call? And the way that we'll answer this question is by looking at the standard deviation. So here's the data. Okay, and this is the data for Mr. Jackson. This is the data for me. And we see that day 1, day 2, day 3, day 4 are all listed in the column. We see how many dinosaurs were caught on each day. We can calculate the deviation. So on each day, hey, how far does that deviation, does that day differ from the mean? And then we can do the square deviation. So first of all, let's find the range. The range in my data goes really from 102 dinosaurs caught on day 3 all the way down to 12 dinosaurs caught on day 1. And so the range of this data is 90. Okay, so there's a difference from my high day to my low day of 90 dinosaurs. And so that's quite the difference. The variance then is found by calculating the deviation and the square of the deviation. Okay, so there's the deviation, which really you'll see is x minus x bar. So it's each day's value minus the mean. So on day 1, I get a negative value because I was far below the mean. On day 2, I get a smaller negative value, so I was a little bit closer to the mean on day 2. On day 3, I was way above the mean. On day 4, I'm back to below. On day 5, I'm right close to it again. On day 6, I'm above. On day 7, I'm way above. So this should be telling you something right away, is that my catching of dinosaurs is not very consistent. And that should be the first clue about what this standard deviation is going to give us. It's going to give us a measure of consistency. So what we do then is for each of these deviations, we square them. And then we take the sum of all of these square deviations. Okay. In one of the final steps, we divide the square deviation by n minus 1 because this is a sample. And so there's 10 days. And so I divide by 10 minus 1. And so what I come up with is that really my variance is 1081.6. And this would be in units of dinosaurs caught squared. So now we want to find the standard deviation, which really is just the root of the variance. And we can take the square root of this, and this gives us S, which is the standard deviation. And it has a value of 32.9. And so what this tells us is that, oh, if my mean is in the 50s, 53.7. My standard deviation, the spread of that mean, one standard deviation of the mean, is plus or minus, 32.9 dinosaurs. So yeah, I catch 53.7 dinosaurs per day, but that value could differ day to day by plus or minus 32.9 dinosaurs. So it really says that a large standard deviation indicates that the data points are very far from the mean. That's what a large standard deviation gives us. A small standard deviation indicates that they're clustered very closely to the mean. So before really we can determine how large my standard deviation is, we need to compare it against Miss Hughes's standard deviation. Okay, so remember, her sample mean was 53.6. And so here are Miss Hughes' value, and I would now, at this point, invite you to go through this and calculate this yourself. Okay, so at this point, again, find the range, find the variance, and then find the standard deviation. Because we need to know how to do this process, finding standard deviation, both by hand, which you're about to do now, and using Excel, which can make the process a lot simpler and a lot faster, but we need to know how to do it by hand first. So I would invite you at this point to pause and calculate the deviations and the square deviations yourself and go through the same process. And so once you've done this, you'll notice the range in Miss Hughes' data is 25. Okay, so a much smaller range than mine. And the deviations for each of these, you'll notice as we go through, are much closer in value to the numbers that I had. So her deviation is much smaller, which means her square deviation, which is simply the square of the previous column, are much smaller than mine as well. And so what this means is when we take the sum of this, 690.4, and we divide by n minus 1, we get 76.7. And the standard deviation for Miss Hughes, if you've done this already, the square root of that number is 8.8, which says a lot. So did the managers, this is the question then, did the managers hire the right person for the job? Why or why not? And of course, what you should be saying at this point is no. Mr. Jackson should never have gotten this job because I'm so terribly inconsistent with my dinosaur catching. Miss Hughes is much more consistent. And so again, we come back to a dot plot and we say, well, my standard deviation is 32.9. Miss Hughes' standard deviation is 8.8. And so if they were looking for a worker who would have a consistent performance, then they hired the wrong person. Because Miss Hughes is much more consistent. Each day she goes out and she catches roughly the same number of dinosaurs. Me, I have very good days and I have very bad days. Some days I catch a lot, some days I catch very few. But if they were looking for someone who is capable of a very high performance, but not necessarily at a sustained rate, then they hired the right person. Because Miss Hughes never really caught more than 66 dinosaurs. So her best day was nowhere near as good as my best day, where I caught like 103 dinosaurs. So here's example 3. Ruben and Dana are laying patio stones. They record how many stones they put in place each hour in an organized table. Okay, so hour 1, 2, 3, 4, 5, and 6. You see Ruben's numbers, you see Dana's numbers. And so we get our total, which is actually pretty close, 236 to 246. So which worker gets more stones put down during the 6-hour day? Well, Dana, because over the course of the day, she puts down 10 more stones than Ruben does. But which worker is more consistent on a per hour basis? And we come back to this notion of consistency being evaluated by comparing the standard deviations of the two data sets. So at this point, again, I would invite you to use Excel to set up a chart just like we set up for the dinosaur example, but set this chart up in Excel. So press pause now, set up your charts, and compare. And when you've done that, now you come back to basically finding, okay, well, you found a standard deviation for Ruben, which is 3.7, and a standard deviation for Dana, which is 8.1. Now, of course, if you're savvy, you can set up the chart just like we did in example number 2, I guess it was, the dinosaur example. And you can do the whole chart, you can sum it, you can divide, you can take the difference, and you need to know how to do that. If you're savvy, you may have looked in the back of our textbook. And the back of our textbook actually gives you the Excel formula which you can enter to just find the standard deviation. And in fact, you are welcome to do that. That's one of the ways Excel can help. It can find the standard deviation for a set of data in one line. And you don't have to do all of that work. But in fact, either method would give you the same answer. Ruben 3.7, Dana 8.1. And so even though Dana then put down 10 more stones, Ruben's performance is more consistent according to their standard deviations. So when we move to grouped data, our discussion changes slightly. Because with grouped data, we don't just have raw data points. We have frequencies, we have midpoints, and we still have means. Right? So once we organize things into intervals, we have to do things that are a little bit different. And of course, the standard deviation for the population and the sample both differ in the same way. You get the n versus the n minus 1 in the denominator. But now instead of just using data points and subtracting them from the mean, we now have to use frequencies and midpoints and subtract from the mean. Okay, so remember that f in these formulas is frequency for some interval. M is the midpoint of that interval. This method, because of course we now know, hey, grouping data, we're going to lose a little bit of accuracy. Using ungrouped data is more accurate. This will give less accurate results. But it's often very, very handy. So use Excel now at this point to calculate the standard deviation for the salaries listed below. One thing you will note is that you cannot, once you've grouped your data, you cannot use the little formula for standard deviation in Excel. That only works with raw data. So in this case, for Excel, you've got midpoint salaries and you've got frequencies. You have to do a chart in Excel. And you will get, it'll still make your life way easier using frequencies and midpoints with Excel, because it does things much quicker and it adds things quicker and you don't have to worry about making silly mistakes. It's not quite as fast as just using a formula. But here, if you want to work on this yourself, you can. Feel free to press pause and just go ahead. But basically, find the grouped mean, right? So you have to find the mean first. You have to find x bar for this data set first, using midpoint and frequency. So you may have to look back in your notes to refresh your memory about how to do that. And then you want to find the standard deviation. And so what you find is that the standard deviation for these salaries, when you've completed the Excel, should be about 10.7. I'd encourage you to save this file. Either that or print it right out and affix it to this lesson so that you have it as a reference.